In this short video, I wanted to talk you through doing the calculations for labS. These calculations are really important, and you're going to see similar sort of calculations in labT and the labX exam, in various other spots, as well as the lecture. So the idea here is you prepared a primary standard of oxalic acid dihydrate. Using that primary standard, you pipetted 10 milliliters, understand that that's 10.00 mils of the oxalic acid, into an Erlenmeyer. You titrated this with your secondary standard, sodium hydroxide. Now, in preparing the primary standard, approximately 0.4 grams was measured out. In my example here, I have 0.4012 grams. Be sure the molar mass that you use for the oxalic acid is that of the dihydrate. So first of all, we calculate the moles, and then we divide by the volume of solution. So you should find that you have a concentration of around 0.03 something molar to four significant figures. Then we do the titration, and I'd like you to assume that I did the titration and I have several replicates, and then I came up with this particular standard deviation, 0.07 milliliters. Please remember that the standard deviation must always be expressed to one significant figure. Given that the standard deviation is to the second decimal place, I am permitted to express my volume of titration to the second decimal place. Please be sure to adjust if that's not the case. That is, if, for instance, your standard deviation is larger, something like 0.2, then you'll need to adjust the volume of your average titration, or the average volume used in the titration. Now the thing is, we want to make use of the standard deviation in subsequent calculations to apply, in a sense, the uncertainty to the final concentration that we calculate for the NaOH. So we're going to find what we call the percent relative standard deviation. Very simple calculation. All you do is you take your actual standard deviation, divide by the average volume times 100%. Again, this should be expressed to one significant figure. Note, however, the decimal place is irrelevant in terms of how you express the average volume. So do not feel like, oh, now I need to cut off the average volume to 16.9, as in for instance, for my case. So again, the decimal place in the relative standard deviation does not impact the decimal place of the average volume, or the average, whatever you're measuring. Okay, so then the next part of the calculation, now that we have the standard concentration of our solution and the fact that we've done the titration and we have a standard deviation and a percent relative standard deviation, is we look at the balanced chemical equation. So oxalic acid reacts 1 mole to 2 moles of sodium hydroxide. You can see that I've set this up kind of like what we do in lecture, in that I have the concentration of oxalic acid, I have the volume that I used, then I have the volume used in the titration, and I'm trying to determine the concentration of sodium hydroxide. So the idea is I'm going to take the concentration and the volume of the oxalic acid and find the amount. And so you can see I've started to do this calculation, and here, volume times concentration gives me the amount of oxalic acid. I then use the mole ratio in my balanced equation to find out, well, how many moles or what amount of sodium hydroxide would be reacting. Now that I have the moles of sodium hydroxide, I can divide by the volume of sodium hydroxide. Students in the lab context sometimes get mixed up in terms of what volumes you should be using. So understand that it was 10 milliliters of the oxalic acid that we pipetted. Understand that it was 16.92 mils that we used in the actual titration. And so when I'm going to calculate the concentration of my sodium hydroxide, that's the volume that I'll be using. So in the end, I end up For the sodium hydroxide, secondary standard, 0.03762 molar. If your numbers are anywhere similar, that is, you used around 0.4 grams of oxalic acid, your titration used around 16, 17, 18 mils of titrant, your concentration of sodium hydroxide should be really similar. All right, so you may recall from the previous slide that we calculated the percent relative standard deviation, and you can see I express it right here. So the sodium hydroxide concentration would be 0.03762 molar plus or minus 0.4%. But what does that 0.4% actually mean? So what we do is we find out what is 0.4% of this particular concentration. So the calculation is 0.4 divided by 100, that's what's meant by the percent, times the concentration. And this gives me a value of 0.002 to one significant figure. So I write that down. But then I look, well, how many decimal places is my, in a sense, standard deviation? Well, it's 4 decimal places. Therefore, I can only express my concentration to 4 decimal places. So you can see I round off to 0.0376 molar. So hopefully this very short video and also the template will assist you in doing the calculations. Again, if you have any questions, be sure to be reaching out.